screenshot that I'm recording eventually. Okay, it said I'm recording, so I think we're good. All right, let's begin today's lecture. So we are going to basically follow up from. Let me wait until my screenshot. Okay, so we're gonna follow up on what we discussed last week, which is out of order processor. All right. Let's review real quick because it's a lot of content. So what we assume so far is any scheduling, any way, any sequence that you may not be able to do it, the sequence of how you execute each instruction, the way we discussed it so far with pipelining in order processor is done in order. The compiler will compile the code into assembly and they would figure out some order and they would stick to that order, line by line by line by line. But if you look at dependency, right? If you like literally draw out the dependency graph, you will notice that you don't have a lot of dependency in many cases. So you can actually run things out of order. If you're waiting for some future data, you can schedule the other independent instruction. And the concept of out of order processing is like, okay, can we do that in hardware? We call this dynamic instruction scheduling. There's actually a lot of techniques after out of order processor to make it even better. If you're curious, I do have a video from last year. I'm not sure. I don't think we have a video for the earlier section of the class because I think I taught it in the advanced architecture in the second lecture. But if you're curious, I can kind of briefly go over that after this class. Just send me an email. You know how it works. Like if you're curious about something that I can answer, I'll answer them. The question that we're asking is basically, can we have the hardware do this scheduling or assist in scheduling? Basically, can we imitate data flow graph, right? And the answer is yes, through the out of order. So let's look at the first thing we have to consider. How do you dispatch instruction not in the order of their arrival, right? And the key here is to basically figure out, is this independent instruction? If it is, you can schedule them, right? So the benefit here is obvious. You can have a lot more, basically a lot more instruction retires per cycle, right? You can tolerate latency of some instruction that are waiting for a while to finish. And these are the key components. Basically, the first component is called reservation station. Basically, we think of it this way: it's a window that hold all the possible instructions you've seen so far. Doesn't have to be dispatched. Basically, a instruction that you fetch and you collect it. And basically, depending on how many you can dispatch per cycle, you're going to try to dispatch as many as possible within a cycle. And this is sometimes called the scheduling window, right? As the name suggests, it's a window that takes in instruction, and you're waiting for the instruction to be scheduled. So this structure, another structure that you need for out of order processor is a way to reorder, and this is a reorder buffer in the write back stage. In the write back stage, these make sure instructions are committed in the order that is supposed to be. Basically, when you are a programmer and you're trying to debug your own assembly code, right, you will then see something predictable. And the MIPS processor, for example, right, how do you play the Nintendo 64 or PlayStation 2? Do you know that they're implemented using the MIPS ISA, the one that you use in the lab? These are real ISA used in real chip. It's actually very popular back in the 1990s and I guess I would say early 2000, but mostly early and late 1990s. This is a real ISA, real program that you can actually run. If you somehow manage to implement everything in the MIPS ISA, I believe there's high chance that you can maybe run, like emulate PlayStation and PlayStation 2. I think MIPS I think PlayStation 2 used MIPS 8,000 or 10,000, one of those two. Uh, but yeah, so the thing you're doing in the lab actually coming from real piece of hardware, right? And if you program, okay, let's go back to our topic. I got overly too excited on something sidetrack. The structure to help reordering as a programmer that allows you to debug your assembly code and know exactly these are the order of things, how they retires. One thing you want to measure is make sure there's no hardware bugs because you need to debug it through the design phase. Right? Once you fabricate the chip, you would assume there's no hardware bugs, and then everything would be coming from assembly. Anything else, you will then need the register aliasing table you will see on the sample exam on how it works. I think going through the example from the last year exam is probably I think the best to teach you how this thing works, because we'll go through an actual example. There'll be 5 instructions that we are trying to run. And the question asks, what are those 5 instructions based on a data flow graph? And time to actually try this out in a proper example in a bit. Dealing with register renaming is as simple as you pick the reservation station entry, right? That correspond to kind of like, okay, this instruction will produce this value. That's it. Information in the register rename table or RAT would consist of the tag, right? The tag of this reservation station entry ID, the value, right? Because you care about, okay, what's the value that I can use? And then the valid bit, can I use the value in there? Or is that all? These eliminate the case where you have the same register from the 2 instructions that has nothing to do with each other. If you recall, we have 2 data hazard, WAR and WAW, right? That can cause this dependency. It's not the dependency that becomes legit in an in-order processor. But if you look at out-of-order processor, you can have write after write and write after read. That becomes a problem because future writes can happen before the earlier writes. Why? Because we do things out of order. So you want to make sure we handle that dependency properly, right? And this virtually enable performance of having lots and lots and lots of register. Even the ISA doesn't give you that many register, right? So it gives you room to use this general purpose register as you see fit. A quick note about number of register. How many of you are familiar with graph coloring problem? The idea of graph coloring problem is if you're given a graph, right, a mathematical graph, how many color can you actually draw on each node so that no adjacent node has the same color. No adjacent node has the same color. And there's a trick in compiler to figure out how many register files do I need? I mean, how many registers do I need to solve my program? You do that through graph coloring, because if you have a neighbor node with the same color, it means there's a dependency of that register number. And you can color the graph to figure out how many registers do I need to actually write the assembly files corresponding to this block of code. So things you learn in algorithm get translated to things in hardware, in compiler, basically everywhere, right? These are useful. And this is related to what we're talking about right now, which is the number of register. And we talk about Thomas Rule algorithm, where if you have a reservation station, if it's available, this is how it works. If the source, basically when you fetch an instruction, you put that in the reservation station. Renaming happen whenever you have an entry in a reservation station. The name that you're renaming is the reservation station ID. The reservation station ID. If the station is full, stall. Why? You have no room to fetch new instruction. Inside the reservation station, you wait for the signal from the pipeline saying, hey, I have the value for this ID. Who needs the value for this ID? That be announced on this thing called common data bus. Basically, it's a wire that gets broadcast. It broadcasts to every component that might need the value. Saying, hey, who needs A? If you need A, here's the value. Take it. After the instruction finish from the functional units, you broadcast the tag, right? A, reservation station ID in the common data bus. Register that contain the tag. Whoever needs the data would grab the data and then proceed onward. If you have all the data available, you grab all the data and execute. If you don't have all the data, you only have the first operand, you wait for the second operand. As simple as that. Basically, you wait for the tag. If the tag becomes ready, go ahead, run your instruction. Doesn't have to be in order. We don't care as long as you retire in order. All right, we went through this example last week, so we are not going to go through the same example. And here's the benefit. It's fast. It imitates the data flow model. The restrict parts or number of entries that you have is a hardware thing, right? It's a hardware thing. It costs an actual transistor. You are given the same amount of die area. The CPU you buy, right? It's about that big. It's about that big. Everything has to fit in that area. Every single transistor you want to build into the chip has to fit into that area. So this actually gets really big. If you look at the design of the CPU versus the GPU, you notice GPU don't do this. GPU doesn't have out of order scaling logic at all. Everything in GPU is done in order. Why? They make trade-off. They want more throughput. They're gonna add tons of ALU. They will assume that the programmer knows what they're doing and write the program that's GPU friendly. CPU is a different story. You cannot assume what people would write on your CPU. It needs to be able to do everything well, right? Because it runs myriad types of program. The way GPU is designed is so that everything would be fast. Everything would be fast. That's why you can do out of order. Because if you think about it this way, in theory, data flow means fast. So you can imitate data flow. So hopefully your program is faster. And remember, we haven't had the memory in this. And if you notice, memory is still one cycle. We'll change it soon. We'll actually start changing it from this lecture onward. Dealing with branch, this is now the content, the new content, right? Actually, not. We kind of covered this at the end of last week. Basically, what if you have branch? Right? What if you have branches and you predict incorrectly? And you do things out of order, which means you might have run future instruction you're not supposed to run. Right? You might run something you're not supposed to run because you predict incorrectly. You already fetched those and you run that out of order. So the first question, what is the state that I have to change back to and how to revert back the change? And the key answer is simple, checkpoint. Similar to when you play a game, right? You go and fight the boss, and the first time I fight the boss, sometimes if it's too hard, I'll lose, right? If you play things like Dark Souls, it's a nightmare. You're gonna lose for the first time, for the second time, for the third time, and you're gonna go back to the checkpoint, the spawn point, basically, then you go fight the boss again. That's what checkpointing is. I'm joking about Dark Souls, so it's kind of notorious for like really, really, really hard boss fights. So if you played before, you notice, you know what I mean. Basically, you create a copy of the future files. This is how you do it in the computer. You create a copy of future files that associate with the branch. If the checkpoint copies are updated, right, you produce a proper register value. And if you mispredict, restore the checkpoint future files. Flush the instruction in the pipeline because those are not supposed to be run. Remove the checkpoints that come after the branch. remove the checkpoint that comes after the branch. And this prevents a stall. Anyone want to take a guess on what might be wrong in terms of security about this? It's actually related to Meltdown and Spectre, the two hardware bugs that we talked about way back in the first lecture.
We can predict the next variable.
So if you think about it, right, you checkpoint future files and you run it, which means that some not supposed to run instruction get run, something get run, right? Which means that if those instructions put the data in the cache, if they put the data in the cache, you need to get rid of those because someone else can come in and look at the data. It's as simple as that. You have a branch, right? A code branch. This is correct branch. This is wrong branch. And somehow you've been running these instructions for a while, right? You've been running these. Let's say this thing put address in my cache or the memory. Basically, a cache is a smaller memory that you use as a temporary thing to tolerate the latency. Basically, you are writing some value to address. You're writing some value to address. It's not committed to the memory. It's already in the cache, which is fine. You just flip the valid bit. It's not valid anymore. No one can use it. But someone can peek looking at that data. Like, hey, what's the data? How can they do it? We call this side channel attack. You look at the electrical signal that gets spit out when you are trying to run your program. So when you run anything, when you run any piece of electrical devices, electron move from one part of the wire to the other, right? And when electron move, it means it generates a magnetic field. It generates electromagnetic field. You can sense the electromagnetic field that this generated. It's as simple as that. You just sense it, and you know, oh, electron move. Okay. Oh, electron move again over here. Okay, and then you keep sensing until you can figure out what is the data. And there are actually multiple papers on this, what we call side channel attacks. That some of them are pretty dangerous, some of them are not as dangerous because some of them assume that somehow you can open your desktop and you can kind of like put the device right next to the main board. And I'm like, okay, if you can somehow get that close to the machine, why don't you just steal the machine? It's the same thing, right? So, but some of them you can kind of sense it from further away, right? And now with IoT, right, a device is going to be everywhere around you. This problem would become a little bit more serious because you are going to have signal that means something going across everywhere in the air. Right? Okay, so now I again get distracted with side topic. If I'm getting too distracted, let me know. But whenever I can say I'll tell you stories that are related to things we learn, I love to do that. I love to like tell you, okay, these are different things that can happen in hardware that you might have not heard of. Okay, so what we consider so far, fetching is one cycle, access the data is one cycle, but that's not true. That's not true. Why? The main memory is actually really slow, about 100 times. I would say 100 times slower than doing one ad. Give and take, basically the actual access might not be that long, but somehow you need to queue up, right? It's like you go get the checkout at a department store, your own shopping cart, it might not take that long, but you need to wait for other people to finish before you, right? So sometimes it generally on average is about 100 times longer than doing one ad, which is about 100 cycle. We'll go into way more detail on why and how to figure out the exact number of cycle. But memory take a long time to access, and you also have limited memory, right? These days you should be able to buy, I would say a 512 GB machine on a server, right? On a desktop, I would say at maximum 64. If you're so rich, that's 128. I think you should be able to buy it. You can do like error correcting DRAM as well. So memory technology is really fancy these days. It's getting better and better and better. I've heard things about like in the future that might be terabyte size memory. In fact, I had a paper last year, right, that would assume that we have 2 TB. Basically, we assume that we have 2 TB. The problem with those is there's going to be so many errors, right? So how do we tolerate all these bit flips? How do we actually make sure they work? Because from the software point of view, you want to make sure all the hardware works. From the hardware designer point of view, we want to make sure nothing fails, at least in the first 5 years. After 5 years, good luck, and you might need to buy your own new machine. But yeah, it should be good enough. So out of all the processing with memory, this is one more thing that you have to add in your pipeline, right? Because the content of the memory has to be updated in order. Again, when you commit everything, it has to be in order. So when you need to store something, it has to be stored in order. There's also dependency between load and store. Future load, what if you do this, right? Store address, and then you load this, right? You store the value R1 into the address. Then from the same address, you load them into R0. If you look at this code, can someone tell me, do I really need to go to the memory and check the value to get the value of R0? Technically, yes. Right? Technically, to be correct, yes. To make sure it's bug free, but can we do better? Because obviously, this is basically you're gonna write the content of R1 to R0, right? At the end, R0 will take whatever R1 is having. So how do we detect, first of all, how do we detect that there's the dependency here? There's a shared address over here, right? This is dependency. And how do we actually bypass some of this dependency, right? So one easy way to do this is maybe we can assume that every single load instruction is always dependent or independent. That's a legit assumption, right? If we assume that everything is dependent, then we stall on every single thing, right? You stall, make sure these are done in order. If you are assuming these are independent, if you're assuming this independent, you don't stall. You speculatively load. Speculatively means that you think that, hey, let's assume that's correct. I'm going to load it. You go and load the data. If it's wrong, then you correct it. Okay. One way you can do this is use something what we call a load store queue. A load store queue. What is a queue? It's a line that consists of items, right? That's what it is. It store, right? It store the load and the store. What do you put in? Information related to that. What are the information? Address, value, and whether it's a read or write, right? Whether you're reading from DRAM or writing to DRAM, what's the value and what's the address? The obvious part is the load can search the store after it knows the load address. Why? If it's there, just take that value, right? Because you are trying to store something that you're reading from later. So take that value, it's faster. The less obvious part is If things are dispatched out of order, how can you maintain ordering? Right? And there are multiple ways you can do this. The simplest one is maybe using a timestamp, right? When does this store get issued? The problem with timestamp is how many bits are you going to use to represent the timestamp? The solution depends on how you want to optimize the design. Basically, there can be multiple solutions. You can have even combined load and store into one queue. And the load store unit is basically answer this question, or can we do other order during load and store? Think of a store as a producer, right? It produces the data to DRAM. The load is consuming the data from DRAM. So if you're producing something, the load is going to consume later, use the data in the queue. Use the data in the queue. As long as you know, I guess, what is address, right? As long as you know the address, then you can load the data if that's the store to that same address. You just get the most recent store from that point of the load. That basically answered that question. What if you're loading something you store earlier? Well, check the store queue. And during a memory instruction, the way you can do this is you first look at the load store type, address, and data. That's how you can predict what are you loading. And then you allow the pipeline to be run out of order, right? Out of order. And load store can be done independently of future instruction because those are done in the memory. As long as we commit everything in the correct order, you'll find. We will talk about this later in the, I think, lecture 10 something about what we call memory consistency. This is an important topic, not just in hardware, but in database system and a lot of things that requires archiving, right? Even things like distributed system, how does Facebook make sure that I see the same a series of updates, series of comments on posts that I put in, right? It ensures this thing called write consistency. It ensures that things are done in order, basically. Everything is done in order. The same concept that we're talking about, we want to make sure the user see things commit in order. Basically, if you have future instruction, need data from this address, forward the data to the load again. The same, so here's an example, right? Let's say we have a load queue, store queue, right? Tag, which is, I guess, address, right? Valid, and the value. So let's say that you have a write to address 0xa0, the value is 10, and that's a store and it's valid, right? And then you are trying to load address 0xb0, well, definitely not valid. You're trying to load it, right? And then let's say there's a future load 0xa0. What do you do here? Basically, the first thing, this request is sent to DRAM. This is also sent to DRAM. Instead of sending this request to DRAM, you go here and say, oh, okay, same address. I'm going to take the value 10. Right? Because there's a store to that address. What if I do another store to the same address again, 0xa0? Now this is valid. This becomes invalid because I overwrite the store. If the future load comes in, right, 0xa0, you see how I update the table, right? And now the most valid version of the address should be the most recent version of the store. And these should be added in order. How do you do that? How do you do that? During the decode, you know what instruction it is. Put it right when you fetch. You fetch decode, right? Decode still have everything in the order of arrival. So once you know there's a load or store instruction, put it there. You just set the value to be 0 because I don't know the value yet. And then you basically figure out, okay, can I look up the value? Any questions about this example? Otherwise, we'll go through the out of order example. So everyone, please open up the exam from last year. Let me pull it up here as well. And we'll do one part at a time, right? But I'll give you time to solve each question. Do you see my screen? Yes, no, do you see my screen? Basically go to question number 5. You can download this from Canvas. It's posted in a file. So you go to File tab. You should be able to locate a file named F19 CompArch midterm. I want you to go to question 5, and right now, let's just do question 5A, right? I'm gonna give you maybe 20 minutes on this, and then we'll discuss how do we solve it. All right? Yes, no, yes, no. I'll give you 20 minutes. If we finish early, we don't need 20 minutes. That's fine. We'll discuss how this is done. Let's do part A first. Part A. All right. So let me mute it myself and I'll shut up so that you can work on a question. And I'll get some water. I'll be right back. All right. All right, let me say ask something. How's everything? Do you at least get the first instruction out? Oh, actually, let me unshare the screen and share it on my main screen. Otherwise, I cannot draw on it. So let me share my own screen right now. Screen number 1. So we should see a bunch of people right now. And now, can you see my screen again? Okay. All right, get rid of this. We can have a better full screen. No, there's a highlighter. All right, let me open this from Microsoft Edge so that I can edit it. Otherwise, I need to sign in. Maybe I need a fancy version of it. All right, so first thing I would do, right? First thing I would do is I'll first label here instruction A, instruction B, instruction C, instruction D, and instruction E. Right? And what are the order that I need to guarantee for sure? These are the order. A has to be done before B, C, D, and E, right? For sure. A has to be the first one. B has to be done before what?
C.
C, D, and E, right? And E has to be the last one. Let me put in the question mark because I'm going to ask that later. But then you know that D has to happen before E. Right? D has to happen before E. B has to happen before D. A has to happen before B. Now the next one is where is C? C has to happen also here after B, right? So if you want to label, let's just label instruction. You know for sure this is A, this is B. And then C, D, E, we'll figure it out. This is the hint. Something use R1. So what use R1 in here? R1 is right here, right? This is R1. So which instruction use R1?
B and C.
B and C, correct? So that somehow has to be R1 in here. And the other instruction that use R1, instruction C, so you can put C here, right? You can put C over there. And now you have D and E left, and you know that D has to happen before E, right? D has to happen before E. You only have 2 slots left, so you can tell that this is D and this is E. Okay. The next most obvious part, A is add. This is multiply. This is multiply, right? This is add. And this is multiply. Okay, so let's get both sources. What are the source of A and B? I mean, of A. Let's just say source 1 and source 2 of A.
5, 6.
R5 and R6, right? R5 R6, and what's the destination? What do I add? What's the result of my add? R1, right? It's right here. This thing produce R1 going into both source, right? Into both the multiply, right? R1. And what's the second input of multiply? R6, yep. It looks a lot. Don't let this confuse you. It's actually pretty simple. How about C? You know that one input is R1. What's the second input?
R2.
R2, right? R2. And what does it produce? R4.
Yeah.
How about instruction D? What's the inputs and what are the outputs? R5, right? And R2. And here is R4. And the last one is I'm going to multiply R4 and write the result back to R4. Any questions about this? No, if you see that R4 as a two inputs, yeah, that's a legit, right? How many of you write a code that say A equals A plus A?
Yeah.
That can happen. I can write A equals A multiplied by A, right? Int A equal A multiplied by A. That's a totally legit line of code in C. And that's what I wrote here. R4 is R4 multiplied by R4. I want to do power of 2, right? It's a power of 2 of R4. So do we have any questions about part A before we move on to part B? So for part B, I'm going to leave you more time. Actually, part B is the one that gets a little bit more complicated. What we say here is, what is everything at cycle 9, at cycle number 9? What is the status of register aliasing table reservation station for the add and multiply at cycle number 9? The trick here is to do it instruction by instruction. You have the list of instructions from the top, so let me browse it on a different monitor. So I have 2 monitors to work with. So let me do the easiest one. The easiest one. You notice that we use R1, R2, R4, R5, R6, right? R1, R2, R4, R5, R6. So for sure, R7 and R0 are not being used. R7, R0 are not touched, are not load, are not, like, if you look at the dependency graph, we don't use R0 and R7. So you can say it's valid. And here's a tag. It's the same R0. If you need R0 and R7, take this value. It's whatever status of R0 and R7 before you go into this code. Okay. What else can I say about R5 and R6? Over here, right? Over here, the only three register that you modify is R1, R2, and R4. You're not modifying anything else. You're not modifying anything else. So you can say that anything that are not here, like R3, R5, and R6, would also not getting modified. So you can write in R3, R5, R6, right? because you are not modifying the content of these value. Even though you use R5 and R6, you're just loading, you're not writing to it. So the register aliasing table maintain the old value. All right, so let me go to the instruction, the first instruction for you. Add R1, R5, R6, right? Add R1, R5, R6. If I see add R1, R5, R6, here's what I would do. If you look at the add reservation station, you see the add, right? You see the add. So let me go to the first instruction. You do the rest. You see the add, and what does this? What is this trying to add? It's not bad. Oh, actually, it's my bad. My bad. My bad. My bad. Let me erase it. So you add between what and what? R5 and R6, right? You are adding R5, the value is R5. Is this valid? Hint, go up. Is R5 and R6 valid?
Yes.
Yes, right? The reason why it's valid, I know the value is R5 and R6. And here you fetch, you decode. I said that add takes 3 cycles. So you have execute 1, execute 2, execute 3, memory, and write back. So you can do write back right away. There's no memory stage. Okay, so at cycle number 6, what can I do? Add modify R1, right? Add modify R1.
Professor.
Right? So by cycle, yes.
Sorry. Can you repeat the first instruction?
Oh, so this is the add, right? Add.
Yes.
So you do this R5 plus R6 equal R1. You basically move this into R1, right? The first thing you do when you fetch, when you're right here, right? You fetch instruction in, you put them in the reservation station, as we said. Once we fetch, you throw that instruction into the reservation station. You grab the first empty station. Over here, entry A is empty, right? So you say, I'm going to add R5 and R6. I'm going to set that as valid because I know the value. What else do I have to do? It modify R1. It modify R1. So I'm going to say R1 is not valid. I'm modifying it at. Entry A right here, it is the entry that if you want R1, go look there. The value is not available. Oh, no. That finger, I'm sorry, not available because I haven't finished the add yet. I have not finished the add, but by cycle 6, I finished the add. So I know what is R5 plus R6, right? R6. Let me do that just to make it clear because it should be R6 over here. You know that is R5 plus R6. So by cycle 6, you can put this here, right? And say, hey, this become valid. And this is R5 plus R6.
Should be
because
R1.
you finish the add, right? Right here. You finish the add, you know that, hey, that's a result. Okay, so I'll let you do the rest. I'll let you do the rest for maybe 20 minutes. We'll be back and we'll discuss how do we proceed to the rest of this question. And feel free to ask me anything in the meantime. Alright, let me check my cat's a bit. She hasn't drank anything in about 2 days, so I want to make sure she's okay. Mhm. right, how's everyone doing?
So we have only one adder and multiply. Are you right? Or we have
So only one add and only one multiply are being executed. So, and oh, yeah, yes. You only have one adder and one multiplier. So if the second add comes in or if the second multiply comes in, wants to use the adder, you cannot use it at the same time. Wait, let me double check the question. Yeah, so you only have one adder, one multiplier. All right, how's everyone doing? We close? Can I do the second instruction? Let me do the second instruction, actually. The second instruction is a multiply. And it multiply R1 and R6 together. So this is what I would do. I put in R1, right, as the tag. And I put in R6 here. Is R6 valid? Is R6 valid?
Yes.
Yes. So you put in R6 and 1. Initially, this is not valid, right? The value of R1, actually, this is not R1. What do you put in here? Well, you can put in R1, actually. My bad, my bad. Over here, you put in R1. My bad. The value is still not available, right? Why? If you look at this entry, right, that's R1, but R1 is not available until cycle number 6. So you can fetch, you can decode, but you cannot execute until cycle number 6. So you can execute it here because now you know R1, which means that I can erase this because I know R1. This is at cycle 6 onward. You have the valid R1, and this is R5 plus R6, right? And you, because it's a multiply, you execute for 4 cycles, and you write back, right? Any questions about the second instruction? Eraser. Any question about the second instruction here? If not, I'll do the third instruction. So what's the third instruction? The third instruction is multiply, right? Multiply R2 and R1. Oh, actually, I forgot one more thing. R1 is okay, but second instruction writes to R2. So over here, you put in X. Over here, you would put in not available yet, right? And this is 0. Why? You're looking at cycle number 9. At cycle number 9, you're still trying to get, right? You're still trying to get the value of R2. It's not done until cycle 10. So in cycle number 9, R2 is still not valid. R2 is still not valid. Okay. Instruction 3, you fetch. When you fetch and decode, once you decode, what is the instruction for instruction 3? Is multiply R2 and R1 into R4, right? So if you put in here R2, what is R2? R2 is, so you put in here R2 and R1, right? What is R2? It's not available, right? Because you're still waiting for X. What is R1? At cycle number 9, again, R1 is available, right? So you get R5 plus R6. This is valid, this is not valid. What's my third instruction? I'm adding R5 and R2 into R4, right? R5 and R2 into R4. So, nope, not valid. I put in B, right? And I put in R5 plus R2. Okay, R5 plus R2 into R4. So is this R5? R5 is, as I said, valid, right? R2 is still not valid. So this is not available. And let's actually replace the not available part, right? Because you have the tag. You know it's R2. So to listen to the common data bus, what is R2? What is R2? X, right? Because you know that R2, if you look here, is X. That's my tag. So I'm going to wait for X. I'm going to wait for X. Right? Oh, actually, my bad. I put in X at the wrong location. My bad. Delete, erase. Eraser. This work. Okay. Put in X right to not highlight. X right here, and this is not available. X right here, not available. Any question? Sorry, I should put X as a tag. X is the tag, but it's not available, right? The fourth instruction come in fetch and decode, so that's the second add, right? And then the last instruction come in fetch and decode. That's the multiply R4 into R4. You multiply R4 and R4 into R4, right? So what is R4? R4 is B, right? It's not available. So you write in tag is B, not available. B again, not available. And you write into R4, so you go into the register aliasing table to update R4. It's no longer B here because at the end of the day is C. That's the last write to R4. So future instruction that comes in that want to use R4, they will notice that that should be C. And that's it for this question. Basically, the rest of this goes to part C of the question. Right? Go to part C of the question, which is right here. Right here. This part, we ask you fill in the rest. Right, fill in the rest. So let me copy over what we had so far. Fetch, decode, fetch, decode, fetch, decode, fetch, decode, fetch, decode, execute, right back. Execute. So this is the same copy from the top, right? And this is where we pause. From here, valid, not valid. Valid, not valid. Tag is R0, AX, R3, say, R5, R6, and R7, R5, R6, R7, because we doesn't modify anything here, is not available here, obviously, because it's not valid. This is R0, it's the same thing. This is R5 plus R6. This is going to be R3 because we are not modifying anything here. Reservation station, let me copy over from the top. Valid, not valid. Valid. 6, 5, 5. And this is R2. Oops, nope, not R2. That should be X. This is X. This is not available. This is R1. Nope, this is R5. This is R5. Valid, not valid. X, B, R1, B, not available because we're still waiting for R4 here. This is because we're waiting for R2. This is done, so it's R5 plus R6. This is R6. This is tag is R5, and this is R5. And this is R6. So this is the same copy from the top, right? So let's continue on. And finish everything. What changes? First of all, this eventually would become valid. Right? Valid. So how would you do that? So I'm going to give you maybe 15 more minutes on how you can do this. Hint is everything finished at cycle 17. Hint is at cycle 17, this is the right back. Okay, should I continue? So actually, let me finish up this because it's recorded, so you can watch it later, and you can fast forward to right now once you have the answer. Uh, Essentially, right, once you have the fully pipeline version, you will notice that you can schedule because this is the multiply and this one is the add. You can do at the same time as there's no dependency. And right back, right? The last one, the last problem is with R4. R4, we have the right after right. So let me pull up over here, right? You have the right after right dependency, which means that basically whenever you look at this cycle, right, when you try to schedule what is D over here, let's finish up instruction 3 and 4, and let's figure out when can I start instruction 5, right? Instruction 3, what it does is, let me check the instruction 3, what it's doing. Instruction 3 is multiplying R2 and R1 into R4. R2 finish right at this cycle. This is when R2 is available, right? So you would then change this part, eraser here, this, right? Everything that need X is updated because X is R2. So you would erase this, erase this. This is valid, this is valid, this is valid. And what is R2? R2 is R1 multiplied by R6, right? What is R1? This is R1. Basically, then this would be R1, which is R5 plus R6 multiplied by R6, right? This is the value of R2. Let me just say this is M. This is the value M because I can't fit M into these small boxes. I'll put M here, I'll put M here. Just note that this is R5 plus R6 multiplied by R6. Then the older version of R4, which get finished right here, right here, and also right here. Is needed by instruction 5. So if you look at instruction 5, this is the last multiply. You need B. Right? You need B, which is the result of this instruction, right? Which is the result of this instruction. B already get overwritten earlier, but once you retire this instruction, which is right at these, this is produce, right? This one produce R4. This one produce R4 that you want, so you can start execute it right here. And that instruction will say, hey, who needs B? Who needs B? And C would come in, I do. I do, because I actually have B in my entry. So the common data bus would declare who needs B. What is B? B is actually X, right? X and R5. X is what? X is R2. Right? X is R2. What is R2? It's this thing. This whole thing is R2, which is equal M. So basically over here, B is, the value of B is M, right? M. And then plus R5. So this is, let's say this is actually N, right? You put in valid, N, and N. This thing eventually, once you're writing back, C, the value of C becomes valid. This is N squared. y is n squared. It's R4 multiplied by R4, and that's m plus R5 multiplied by n plus R5, and that's n squared. That's it for the question. Basically, we are not actually, if you look at this last question, you say, I'll say here, just use this table if you are needed. This is the only one I'm gonna grade. Basically, I would just want you to notice that, hey, this is when, this right here is when you have B on the common data bus, right? Common data bus that get declared over here. Who needs B? And then C would come in, hey, I need B. What's my value? When I have B, sorry about this, that's wrong. Let me correct it real quick. It needs B and the value is N. Needs B, the value is N, and that's valid. All right, so that's for this question. You can go through the rest of the question for other stuff, right? For other stuff that get asked last year, things like branch prediction. There's a question on Lodestar unit. There's a question on Amdahl's law. What else? There's a question on branch prediction. There's a question on ISA. Let's say I'm gonna come up with like my own dummy language, and given this bit pattern, what is my instruction? If you did your lab, the assignment 1, you should be able to breeze through the question. Actually, it would look, all the questions we have here would look intimidating if you look at it for the first time, but if you think about it, it's not that complicated. Everything can be done step by step. So don't panic. That's my advice. Don't panic. Let me stop sharing the screen here.
I've got a question about this one.
Yeah, sure.
We started in cycle 13 with next multiply. How can we do that if we only have one multiplier? Because the other one is still going, I think, from instruction 3.
Oh, yes, that's a good point. I made a mistake. Yes, it should be one cycle afterward. Thank you so much.
Okay.
Yeah. Please, thank you so much for correcting me. You only have one multiplier. It's occupy. But did I say multiplier is fully pipeline? Let me check my question a little bit. Okay. So we can do this because I said it's fully pipeline right here. Fully pipeline, including the each stage. Basically, everyone add and multiply only both the adder are okay. Both adder and multiply are fully pipeline. It means that every time I go to each stage of my adder and multiplier, if I have no data dependency, I can schedule it. So you can do it like this. So this is okay. Basically, this E corresponds to the first stage as this E. That part of the multiplier is free. The reason why we cannot do it earlier, because this thing produce R2 and this thing consume R2. And R2 is not known until you are out of the multiplier. But in this case, you need R4. And R4 is produced right here. Produce R4. So by that point, you already have R4. You have a fully pipeline multiplier, so you can put it in the multiplier. Basically, the first E1. Basically, this is E1, E2, E3, E1, E2, E3, E4. This is E1, E2, E3, E4. This is E1, E2, E3. E1, E2, E3, E4. E1 corresponds to the same stage of E1 in the multiplier. If no one is using E1, you can use E1. That's what it means to have a fully pipeline adder and multiplier.
Ah, okay.
Yes.
Thank you.
All right, so that's a great question. Let me save this. All right, so let's go back to our slides. Okay, it's the wrong screen, so let me unshare and share the correct screen. Screen 2. All right, so we went through the example from the exam question. Let's talk about the rest. If you went through the exam, let's talk about the rest during the office hour if you want to drop by. And then let's switch over to memory hierarchy, which is what we will talk about going forward. This is not going to be on a midterm. Memory hierarchy will be on after the final, at the final, in final exam. And we always said, hey, programmer should have unlimited memory somehow magically. I would have all the capacity. It should be contiguous. I should not be able to notice that there's a jump in address space. I should be able to use the pointer freely. I should be able to have a really fast memory, like we assume, right? It's one cycle. So hopefully, how can we make it close to one cycle? The reason behind that is both the OS and the hardware kind of work together to give this illusion. The combination of how DRAM is operating plus virtual memory give all this illusion. Inside the hardware, actual DRAM is a physical thing. And this is what we want from memory. Zero latency, unlimited capacity, zero cost. You want it to be free. Somehow you go to the hardware store, want to buy a DRAM, and they say, hey, I'll give you this for you for free. That's not true, but ideally you want zero cost. Allows multiple parallel access, or this means unlimited bandwidth. You want as much bandwidth as possible. All of this demand, if you think about it, it conflict with each other. If you want a really fast DRAM, it would cost more. If you want higher capacity, it would cost more. It would be slower. If you want more bandwidth, this would cost more. Sometimes this becomes slower as well. So look at all the first four bullets and their conflict, right? How can we actually get the best of everything? Here's the current memory technology. There are two, or right now, three main technology. The first one we call SRAM, or static random access memory. It's fast, but it's really costly. So if you buy a CPU, you will notice sometimes they say that it has this much L1 cache, L2 cache, and L3 caches. These are SRAM. It's fast, but it's bigger. It consists of 6 transistors per cell. Per 1 bit, it requires 6 transistors. DRAM, dynamic random access memory, this is what you buy. Basically, when you go to a computer store and you say, hey, I want to buy a memory, this is what you get. It's cheaper, but it's slower. Think of it this way. SRAM comes with your CPU. When you buy an Intel CPU, it comes with the SRAM, it's on chip. DRAM is off chip. That's what you buy. That's what you buy when you buy like Hynix SRAM or all the different brands of DRAM. Those are DRAM. Here's as I said, it consists of 6 transistors. You need 2 functionality. The first functionality is to store the charge, right? Store the electrons. And you want to be able to access whether it's a high voltage or low voltage. You use 4 transistor for storage. Basically, we call this a cross-couple inverter. It looks something like this, which kind of like force the electron to like move around in the loop. That's how you can store it. And it would keep like these inverter would keep, how should we amplify the electron to make sure it stays in there. it stays in there and kind of like don't leak out. And then you have two transistors to open this to access them. And that's why it considers 6 transistor. DRAM, a little bit simpler. Transistor right here that connects to a capacitor, right? This is ground. I think I draw it wrong. So let me actually refresh how to draw a DRAM. So I think I draw the transistor wrong. I think it's something more like this. And this is the capacitor, and that's the ground. You have 2 wires coming in to access the content of the capacitor. And this is your transistor. The charge inside capacitor stores 1 or 0. And obviously, how many of you use this or seen the, what's it called? The camera you put in a car, so that you keep recording the video footage in case you run into an accident or something. Those things, some of them use a capacitor. And one thing that you might have noticed is for those capacitor-based model, if you power off, if you turn off the car, the power goes out. Why? Electron moves out, literally. Even though it is intended to store electrons, over time it would move out. We will talk about how we deal with this leakage. We call this leakage, basically charge leaks over time. And DRAM has to be refreshed, which means that periodically you need to overwrite the same value again and again and again to maintain the charge, to maintain the value. Otherwise, ones would become 0 because electrons move out. So you can see that there are trade-offs with SRAM and DRAM. First of all, SRAM is faster. Usually it's within like a nanosecond. So if you look at Intel spec sheet, right? If you look at Intel spec, L1 cache, it would be around 4 cycles. L2 cache would be around 10 cycles or 11 cycles, something around that number of cycles, depending on which chip you're buying. Different i5, i7 model from different generation would have different number of cycles for the cache. DRAM is cheaper. It's cheaper. In terms of how long it takes to access, is much longer. But you get gigabytes of DRAM. In the SRAM cache, you look at like megabytes of SRAM cache. In DRAM, you look at gigabytes of those. And then we'll also cover this emerging memory technology, where this is the 3rd type, right? Non-volatile DRAM. This is the memory that doesn't leak. It has a lot more capacity than DRAM, but they are slower. One of the non-volatile memory is SSD. One type of that is SSD. There exists a technology where you can change the cell so that it's a lot faster than your SSD. And right now, a lot of companies are considering this as an alternative to DRAM or the last layer of memory after DRAM. You can have also 3D stacked DRAM. You have DRAM on top of each other. If you buy GPU that are coming out in recent years, and I think they come with some form of 3D stacked DRAM. I'm not sure how many they stack them together, but basically you can fit more DRAM onto the chip or onto the memory module. So our question is, okay, we want to be greedy. How can we get both fast and large memory, right? Fast and large memory. The idea is this. Well, you know that SRAM is fast, DRAM is slow. So why can't we have multiple levels of memory? This is called the memory hierarchy. You start with a really tiny L1 SRAM cache, the level 1 cache, followed by a smaller L2 and L3 cache, right? And then you use a large DRAM as a main memory and would look something like this. You have a CPU core. If you want to load or store something, you check, hey, is my data in the L1 cache? If it's an L1 cache, I will spend 3 or 4 cycles to get my data. 3 or 4 cycles is way better than 100 cycles, right? Which means that memory state, right? Instead of 100 cycle, you use the cache. If it's in the L1 cache, this go down to 3 to 4 cycle. It's a lot faster, right? So you want your data to be in the cache. This is actually matter when you write your own program. You want to make sure your program stays in the L1 or the L2 as much as possible. So this is like maybe 4 cycle, this is around 10 cycle, and this is around 100 cycle. You can see how much time, how much additional time you would need to access the next level of the memory. And when you program, this is visible to programmer. And these two typically is not visible. Why I said typically? GPU allows you to use this a little bit. In CPU, you don't. The hardware manage everything. But you can write the program to make sure you get a better hit rate. When I talk about hit rate, it means that the data that you're trying to access is in the cache. We'll talk about this in detail after the midterm. Next week, it's all about review. It's all about you come in with the questions, and we will maybe go through the exam question, other exam questions together. Afterward, we talk about memory. I want to give some primer on this. Memory locality, basically, if you look at the program, they typically have locality. How many of you write code this way? How many of you write your code this way? All of us, including myself, right? And you notice, first thing, that is we call temporal locality, the value I. This I get used all the time. The same variable, whenever you access it, it tends to get used again. So this is what corresponds to the variable I. Spatial locality means that if you access something, the neighbor location is likely to be accessed in the future. This is A of I, right? Because the first cycle is A of 0, the next one is A of 1, the next one is A of 2. So you can see that, hey, I'm gonna access A of 3 if I access A of 2. That's called spatial locality. And the idea is to use the cache or the fast memory to take advantage of this observation. If I use something, I'm likely to use it again. So here's the basic, right? Basically, data is likely to be accessed again. So you can have this in the paper from 1965, we call it slave memory. These days we call it cache, right? You can take advantage of both the temporal locality and spatial locality. These days we take advantage of both of them in our cache. You notice it's 1968, these days 2020, the cache technology improved quite a lot, right? It's quite a lot to the point that if you come to me and say, hey, I want to work on caching, I will tell you, be careful, because that area was super crowded 20 years ago. So there's not a lot of novelty that you can add on top of it. These days, the way you think about cache change a little bit, so it can be interesting. But in terms of designing the cache from the hardware point of view, it's been hammered by multiple papers in the past 50 years, actually. So here's some example, right? Let's say you want to buy something. Let's say I want to buy milk, right? Think of it as the source of the milk is from a farm, right? It's from a farm. So if I really want to buy milk, one way I can do is go all the way to a farm and go talk to the farmer. Hey, can I buy a gallon of milk? Right? And it would be slow because I need to travel all the way there. Typically, think of large cash as a supermarket, like Big C Lotus, right? Where you can go in and you are expected you can find the milk. It's a common item. Everyone uses it. That's low quality. Everyone buys it. So it's likely that we would stock the milk in the supermarket. Even better, because it's so common, if you go to nearby 7-Eleven, you're likely to find a milk, right? This is the lower level cache. And when you bring the milk home, you put that in the register files in the fridge, right? So this is an analogy of how caching works. When you want milk, you don't have to go to the source, which is the main memory where the milk is produced. You go to the 7-Eleven or supermarket, you put that in your fridge. You can use it in register files until you no longer need it. If the 7-Eleven doesn't have milk, then you can upgrade. Check supermarket, right? And you can manage the cache manually. If you, for example, if you play with how browser manage the website, they would cache, right? They would cache some history of website you visited. These web-based cache are kind of done manually by the programmer. Programmer manage the data. In hardware, these low level of data, the one that you load and store, these are done automatically by the hardware. We built the policy and say, do this policy because we run it across so many applications and it's good. There are policies we'll discuss in this class. And programmer only have to deal with memory references and magically it becomes faster. As simple as that. When you write a program, you can write a cache-friendly code, but you don't have to manually control your program. And why you should care about memory. This is where most program becomes slow. This is where most of your program becomes slow. So if you want to say run a startup company and you want to scale your workload, you would want to look into the cache. How do you actually utilize the cache better? Many of your projects, if you want to be energy efficient, if you want to make it faster, like both Graph and Slam workload, look at their cache locality is always a good place to start. How many times they actually have to visit the memory versus visiting the cache. That can make things a lot faster. And these typically become more complicated when you have sharing, when you have more than one entity sharing the cache, right? But you get more performance. We are approaching this thing we call memory wall, how much we can scale transistor down. Right now we are at 10 and 7 nanometer, depending on the company you're talking to. 7 nanometer per transistor, think about how many electrons you can hold in there and how much you can go down, right? It's not much. So we call this memory wall. You can also have a virtual memory system to make programmer life easier, but they can also slow things down. So we'll discuss this design. And you can be a much, much, much better programmer if you know how memory works. That's my message before we dive deep into the memory subsystem. That's one of the area I'm really comfortable with. Is like my research group back at CMU is one of the forefront of the world. Like we are doing like crazy things onto DRAM. So I'm gonna try my best to translate what I know after the midterm. Typically, we would spend in a normal architecture class, we would spend half of the class on memory as well. That's where things get slow, basically. And I'm gonna do my best at telling you how DRAM works. But before we leave today, actually let's discuss the paper afterward. After we discuss how's everything in projects week 2, I guess you're still trying to figure out, okay, these are stuff that you want to do and you're gonna try to figure out your schedule. Basically, I'm gonna do it later in the semester. Feel free to let me know what's going on. Feel free to let me know if you have any question on the second lab. Pipelining is not as trivial as the first lab. it's the same thing. Once you know what you have to do, you know what you have to code in to do what you want to get. But you need drawing. You need to make sure you draw things and understand this part feed the data into this part feed the data into this part. It can be confusing. Midterm, September 29th, as we discussed, let's ask this. I have a choice for you. You can do a take-home 24 hours exam, open everything. I would give you, so if you took IoT with me last semester, Lucas, you know how the take-home format works. I give you a question, 24 hours later, you submit me the question. You can do at TGGS 3-hour exam. I would come in, we all come in. If it's 3-hour exam, I would do it in room 802, which is my office. We have a living area in the middle. I'll bring in tables. You would do an exam in there. The reason why I want you to do an exam in my office, I have snacks in my fridge. I have coffee machine. Feel free to use them. If that makes you up and awake, feel free to use my coffee machine and my pots. Basically, everything there is for you. Use my fridge, there's snacks in there. You have 3 hours, you can bring in 4 sheets of paper. It's almost like open everything, but you just cannot bring your laptop. Bring in 4 sheets of papers. The reason why I kind of like the in-class exam is because when you make this cheat sheet, the 4 sheets of paper, you learn a lot. If I am forcing you to go through everything. If it's open everything 24 hours, I know because I've done this before, I tend to study less because I feel like I can check the internet, which is true. You can check the internet, but good luck trying to find the answer. You know this, like it is not easy to find the answer. So in the end, it would take more time to finish the 24-hour take-home exam. And it will be a lot more efficient if you do it in a 3-hour exam slot where I proctor you guys and you have access to water, coffee, snacks. So your choice. Should we vote now? Okay, who wants what? Anyone wants the 3-hour exam, so we're done with it in the class slot, and that's it. You don't have to worry about it at home. Raise your hand. Okay, Lucas. Opat. Okay, we have at least 2. I cannot see someone. Everyone said 3-hour exam. Perfect. So we'll meet in person September 29th. I'll be in the lab. I'll proctor you guys and I'll bring snacks. I'll make sure you're full. And if you need to use the restroom, we have the restroom in there. So I'll make sure it's convenient for everyone. And at least I'll make that part pleasant because the exam is not going to be pleasant. It's not going to be fun. I mean, non-exam taking thing is fun, but bring in 4 sheets of paper front and back. That's a lot of pages. That's 8 pages worth of thing. You don't have to use all 8 pages. I want to give you essentially unlimited number of pages. Bring in whatever you want. You can even print like the slide that you don't want to write in like small font size. Do whatever you want with it. Room 802, not 11th floor, my office. So that you have access to all the things that I have. All right. Anyone read the paper that you want to present? I mean, each one of you just have to do it once more. So if you don't want to do it this week, it's fine. I apologize for haven't give you guys feedback on the review yet. I was kind of like busy with my wife flying in and quarantine and everything, and I would do my best to catch up. So by the end of this weekend, I think I should be able to like kind of like give you all feedback, plus finishing up your midterm exam so that you can ask me the question next week and I know what is in it or not. So anyone want to take the slot to present the paper, or should we just call it a day? Everyone is muting. If someone is saying something, you need to unmute. Otherwise, I will assume that everyone wants to call it a day. call it a day. Okay, so we finished earlier. If you want to meet, okay, now that we have time, one thing we can do is to go through one more question on the exam. Or we can do it next week. Basically, this week and next week will be review session for your exam. You can take a look. So how about this? You take a look at the exam questions. If you have any questions, comes with questions. We can go through them next week. I promise it would take less than 3 hours because I'm sure I can finish it in less than 3 hours while at the same time explaining to you what's going on. Right? So please, next week, please check out the exam because if you have any questions, I can answer in class. And we'll go through reviews of everything. I'll list out topics. And then you can ask me questions on topics that you forgot, so we can go through them again. Sorry about finishing up earlier than we thought. I thought it would take longer time to finish up the exam question on the out of order processor, but then I myself say, hey, let's continue on too fast. Any questions from today? No? Yes, no? Okay, so let's meet tomorrow. I mean, not tomorrow. Let's meet next week. If you have any questions about the project, about the lab, feel free to type in on Discord. We don't just have the voice channel, we have the chat too. So if you somehow say, hey, Ajahn Rashata, do I have like time on this slot that we can go over things together? Yeah, just let me know. If I have time, I'll let you know. I would make time for you. I just need to make sure it doesn't conflict with anything in my calendar, right? Because if I have already a meeting over there, I'll tell you, okay, how about this time? Are you free? Then we can meet. I'm pretty open to meeting all of you guys anytime that I'm free. All right. Okay, awesome. Thank you very much for joining in. Sorry about again being done. I think 30 minutes earlier than planned. If you have any questions, let me know. All right, and since Lucas asked this during office hour, the number of reviews is 8 in total to get the full credit. Anything more is extra credit. So it's less than last year. So if you talk to students from last year, like, okay, I think you have to do 9 of them. This year is 8, but you have to do the lab, which is a lot more work than the review. All right. So remember, labs due next Thursday, if I recall correctly. So don't forget that. Is it next Thursday? Let me double check. I don't want to put in a wrong number for you.
No, I think Tuesday.
Tuesday. Okay. Perfect. Yeah. Basically, whatever day I put in on the PDF. Sorry about picking the wrong date. Assignments. Yeah, September 25th. So, oh no, September 22nd. So next Tuesday, you have 1 more week to work on it. If you have not started, please start now. Please start now. If you have not started, if you started already and you have questions, please ask it as soon as possible. I check Discord periodically. So whenever I see questions, I'll come and answer your questions. And if you somehow to be online during the time, I'll also say, hey, let's chat. All right, that's all for today. Have a good rest of the day. Bye.
Thank you. You too.
Thank
Bye-bye.
you.
So,